Let's finish the second example regarding doing a significance test for a population mean. Is there evidence that AP Stat students at Westfield High School score differently on the actual AP exam versus the mock AP exam? Well, using a random sample of 19 out of 195 AP Statistics students. So let's stop right there and show you the data. This is the real data. So something important to consider. There is only one random sample. Here is our random sample of 19 students, and these are, of course, I took their names off, so these are their subject numbers. These are their mock AP scores. So in the past, Mr. Peters and I have given a mock AP exam, which used both multiple choice and free response questions because we want students to have an idea of what to expect when they take the real AP exam. And our hope is that we score the mock AP exam in a way that's genuine, which might reflect what they may actually get on the real AP exam. So for every student, we have their mock score and their actual score. But what's interesting here, what we care about here is not the mock scores. It's not the actual scores, it's can we detect a difference? So, do we have evidence that students score differently on the actual exam versus the mock AP exam? So, the truth is, Mr. Peters and I want the mock exam to be a genuine representation of the real AP exam. But the truth is, maybe we're scoring it too easily. Look at subject number 8. Their mock score was a 4. They got a 2 on the actual exam. So maybe we're scoring the mock exam too easily. The mock exam score was higher. Of course, maybe it's the other way around. Maybe we're scoring the mock exam too harshly. Here, this student got a 3 on the mock exam, but they ended up getting a score of 4 on the real exam. So what we are hoping is that the mock exam gives you a genuine representation of what you might get on the real exam. So here's subject number 68. They scored a 3 on both the mock and the real exam. So what we're really interested in here are the differences. If the scores are essentially the same on the two, the difference should be 0. So if we take the actual minus the mock scores for this first subject, 2 minus 4 is -2. So a negative difference means the mock exam score is higher. So a positive difference here would suggest that the actual exam score is higher. So understand, in this context, I'm not worried about the individual mock scores or the individual actual scores. What I'm interested in are the differences. That's what I really care about. So we have one random sample, and it's a random sample of differences. So 19 out of 195 AP Stat students were actually randomly selected, and the mean of the differences between the actual and the mock exam scores is -0.63. So you don't have to take the time to do this. So if you entered all of these data into a list and did one variable statistics, you will get an average for the differences of -0.63, and the standard deviation of the differences or 1.12. So we see this happen on the AP exam where you are presented with the data, and then you are also told that the sample data, they have no outliers, and if you look at a graph of these sample data, they don't really show any serious skewness. It's important that those two things are told to you. It saves you a little bit of time because you don't have to graph it yourself, and you'll need that information when you are writing about the conditions. So understand, we are interested in this parameter, the real mean of the differences. So I'll write it this way, mean diff. That's the way that I will represent our parameter. So that is the average difference between the actual and the mock AP exam scores at Westfield High School. So the null hypothesis here, I'm looking for evidence of no difference. So differently simply means we're interested in comparing to 0. So guys, if Mr. Peters and I if Mr. Peters and I are doing a pretty good job of genuinely representing the actual AP rubric, then we would expect a mean difference of 0. So we're looking for evidence of a difference that's other than 0. So differently does not indicate a direction. Maybe the mock exam scores are too low. Maybe the mock exam scores are too high. So this is a double-sided test. I'm looking for an average difference that's not equal to 0. And yes, I can see that my sample mean is less than 0. I understand that. But the idea is this extreme enough for us to be able to reject this null hypothesis in favor of the alternative? So, in terms of the conditions, randomness, it is a random sample. We have a random sample of 19 students. (19 AP Stats students). So for independence, you'll see why I selected 19, because 10 times 19 is 190, and that's less than or equal to 195. That's the number of AP Stat students. Now, the advantage of selecting a sample size of 19 is it meets the 10% rule. The disadvantage is that it doesn't meet the normality condition. This is about means. So the truth is, I would like a larger sample size for the central limit theorem to apply. I would want samples of size 30 or more. This is a smaller sample, but that's still okay because there aren't any outliers in the data and we don't see any serious skewness in the data. So even though the sample size is small, even though 19 is less than 30, there are no outliers. Or serious skewness in the data. There are no outliers nor serious skewness in the data. In the sample data. So what that means is we can still use an approximately normal sampling distribution. So the test name, this is still a one sample t-test. So you could call it that. So because we have one sample of differences. One sample of differences. Another name, though, for this test is we have paired data. Sometimes this is called a paired t-test because I have one sample of subjects, but I have pairs of observations for each subject. I'm looking at their actual versus their mock score. So sometimes this is called a paired t-test. Again, I'm looking at a pair of observations for each subject. So I still need to describe the t-score, the degrees of freedom, the p-value. We can get all of that off of our calculator, no problem. So this time I have not entered the data into the calculator. So we're just going to use the regular t-test option. It doesn't matter whether it's a one sample or a paired t-test. Either way, it's just a t-test. So we're going to enter our statistics because I didn't enter the data into a list in the calculator. So when you are working with paired data, you are almost always looking for evidence of a difference or evidence that your paired data is that the means are greater than 0 or less than 0. It is very common to compare to 0 like we are doing in this context. So we will use our null hypothesis value of 0. So again, using the data from our sample, the actual mean of the differences is negative 0.63. The standard deviation for the differences is 1.12. The sample size is 19. it's important to give the calculator the sample size so it can calculate the degrees of freedom, which will be 18. This is a two-sided alternative. We are looking for evidence of a difference, so we need to suggest the not equal to alternative, and then we can highlight calculate. That will give us our test statistic, our t-score of negative 2.45. That will give us our p-value of 0.025. So here's the sample mean and the sample standard deviation that we entered, and here's the sample size. So I'm going to write those down here. The t-score is negative 2.45. Degrees of freedom, 19 minus 1 for 18. And the p-value. The p-value is about 0.025. There we go. So you could call this a one-sample t-test, but I think more commonly this would be called a paired t-test, simply because you have to think about this as one sample of differences, or you have pairs of observations where you are working with the differences between those observations for each subject. So you have to give your test statistic, which for means would be t-scores, degrees of freedom, 19 minus 1 is 18, and then the p-value the calculator gave us. So notice, just for the sake of being able to write a different kind of conclusion, notice maybe for some reason I'm concerned about committing a type 1 error, so I want to lower the level of significance. I'm going to use a level of significance of 1%. So if you are given a level of significance, you should use the one that's given to you. If you are not given a level of significance, I would suggest that you use an alpha level, a significance level of 5%, and you should state that when you write. So here, this time, that p-value seems low, but I want to avoid committing a type 1 error. So that means I'm using a lower level of significance. I'm making it harder to reject the null hypothesis. I'm trying to avoid type 1 errors. So a 0.025 is greater than 0.01. So this is not unlikely enough for us to reject the null hypothesis. So because of this comparison, we don't reject the null hypothesis. We don't reject the null hypothesis. So, based on this level of significance, an alpha of 1%, this is not unlikely. So we do not reject the null hypothesis. So we don't have evidence. Evidence of what? Well, go back to the context. We don't have evidence that AP Stats students at WHS score differently on the actual versus the mock exam. You can literally use the words in the question. If you wanted to describe this, you could say that we do not have evidence that the real average difference between actual and mock exams is different from 0, but that seems more awkward. I would just copy the words. So we don't have evidence. Instead of, I will say, I will copy the words. We don't have evidence that AP Stats students at WHS score differently. On the actual versus the mock AP exam. It is okay. It is okay to copy the words in order to put context into your conclusion. So I was trying to, if you will, show you how to write your conclusion. On the first example, we did reject the null hypothesis, so I wanted to do an example where we didn't reject the null hypothesis. So by lowering that level of significance, we're making it harder to reject the null hypothesis. So we're making it harder to commit a type 1 error. A type 1 error would be that we have rejected, but we shouldn't. We're making it harder to commit a type 1 error. So notice in this case, we don't reject the null hypothesis here. Well, the type of error that's possible here in example 2 would be a type 2 error. A type 2 happens when you do not reject the null hypothesis when you should have rejected the null hypothesis. So in this context, have we made an error? I'm not sure. But if you don't reject the null hypothesis, the only possible type of error that you could have made is a type 2 error. You didn't reject the null hypothesis. So you don't think you have evidence of a difference, but hey, maybe you should have rejected the null hypothesis. If you should have, then you've committed a type 2 error. That's the one that's possible based on the way that we interpreted this significance test.